So let us start the lecture on Galois theory. This is the fourth or fifth one. In the previous lecture, we have seen that if we have a field of complex numbers and a field of real numbers, then we have computed the group of automorphisms which fixes the real numbers, and we have seen that that group is consisting of only two automorphisms. Okay, so this we have seen. If K is the field of complex numbers, and F is the field of real numbers, then we have seen that this group of automorphisms which fixes the field F, the real numbers, is consisting of two automorphisms, sigma 1 and sigma 2, where sigma 1 they are automorphisms of K, where sigma 1 of A plus iota B, it is the identity, and sigma 2 is the conjugate automorphism. A plus iota B is equal to A minus iota B. Now we try to find out the fixed field with respect to this group of automorphisms. Now we find this, the fixed field of this group of automorphisms GK. Okay, by definition, हम definition देखेंगे, फिर हम बाकी चीजें देख लेंगे क्या है. By definition, this K of GKF is equal to those elements of field K such that they are fixed by every element of G, such that sigma of A is equal to A for all sigma belongs to GKF. This is the definition. Okay, so it means that so A is in K means A is a complex number. Okay, A is alpha plus iota beta. इस पेज को मैं इरेज करूं?
Yes, sir.
Okay. So in the last line is last line was this: KGKF is equal to those complex numbers such that they are fixed by automorphisms of G, and G contains only two automorphisms. That's one is the sigma 1 of alpha plus iota beta is equal to alpha plus iota beta, and sigma 2 of alpha plus iota. एक तो आइडेंटिटी इसमें ये तो फिक्स करेगी सबको, it's equal to alpha plus iota beta. Now we'll concentrate on this because this one is the identity. So now this, what is sigma 2 of alpha plus iota beta? By definition of sigma 2 it's equal to alpha minus iota beta, जो हमने भी देखा. So which implies that, but since sigma 2 is in fixed field, it fixes this. Alpha plus iota beta is equal to alpha minus iota beta, and this will give beta alpha and alpha will go. This will give twice iota beta is equal to 0, which gives our beta is equal to 0. So thus in this GKF alpha plus iota beta it's the set of the numbers alpha plus iota beta, the complex numbers having this property. But from these equations we obtain beta equal to 0. So therefore what is this? And we don't have any condition on alpha. Alpha is any real number. Okay, KGKF is equal to the set alpha, okay, such that this alpha obviously it is in F. Okay, so it means that it is equal to F. It is equal to F. But this is not true in general. The fixed field of GKF need not be equal to F in general. In general it is not equal to F. Okay, and we will see that this fixed field KF it will contain at least F. F is subset of this field actually. So here in this case they are equal, both are equal, but in general it contains it. Next example, we will see that this KGKF need not be equal to F. It is sometimes it may be equal to whole K. वो भी हम प्रूव करेंगे. इट्स F is actually subset of KGKF. वो हम नेक्स्ट जो इसके बाद जो एक्सरसाइज आ जाएगी उसमें हम उसको प्रूव करेंगे. बट इन नेक्स्ट एग्जांपल वी विल सी दैट this KGKF it may be equal to whole K sometimes. That's the next example. So next example. Let F naught be the field of rational numbers. Let F naught be the field of rational numbers, and let K be the smallest field containing F naught and cube root of 2. Okay, where this stands for its cube root of 2 is the real cube root of 2. Okay, is the real, because cube root of 2 it may be complex number. In fact there are two complex numbers whose the cube is 2. So actually cube root of 2 has three values. One is the real value and the other two values are complex. Okay, so here we are taking only real values. Okay, where cube root of 2 is the real cube root of 2 is the real cube root of 2. Now we know that we know that what are the elements of K. Actually we know that you had done. We know that this K is actually it's of this type: alpha naught plus alpha 1 cube root of 2, then its square, plus alpha 2 its square, cube root of 2 its square, plus alpha 3 its cube, then that will be 2. तो ये यहाँ पर ही खत्म होगा, जब तक ना इसका ये अगर रैशनल नंबर बन जाएगा ना तो वहाँ तक आपको नहीं जाना. रैशनल नंबर से पहले एक स्टेप, क्योंकि रैशनल नंबर से ऑलरेडी के में है. So where these alpha naught, alpha 1, alpha 2 they are all rationals. Okay, they are all rationals, क्योंकि नेक्स्ट पावर जो होगा ना वो रैशनल नंबर होगा, वो इस अल्फा नॉट के साथ क्लब होगा. फिर जो इसके बाद वाला पावर होगा वो अल्फा 1 क्यूब रूट ऑफ 2 के साथ क्लब होगा. फिर जो नेक्स्ट और पावर होगा तो ये यहाँ तक ये पावर्स आ जाएगी. So K is of this form, where alpha naught, alpha 1, alpha 2 they are all rationals. Now first we check the automorphisms of K. वो किस टाइप की automorphisms होगी. Okay, Then we find the automorphisms of K which fixes F naught. Okay, first we'll try to find out the nature of the automorphisms of K. F naught is the set of rational number. इस पर हर कोई automorphism fix होगी, but it is F naught of Q root of 2, so it's the extension of F naught. So we want to find out, और इसकी जो K पर जो भी automorphism होगी वो determine यही करेगी Q root of 2. Q root of 2 पर इसका वैल्यू क्या होगा, एक्चुअली वही हमें चेक करना है, बिकॉज वी नो दैट ऑन F naught every automorphism is identity. Okay, so F naught तक तो हर कोई फिक्स ही होगा. So let sigma belongs to out of K. Okay, is an automorphism of K. Then we'll see this sigma of cube root of 2, its power cube. So by applying automorphism, it's equal to sigma of cube root of 2, sigma of cube root of 2, okay, 3 times sigma of cube root of 2, and this is equal to, okay, this is equal to sigma of cube root of 2 whole cube. But on this side, if we can cancel out this cube root and cube, it's sigma of 2. Okay, sigma of 2. So which implies sigma of 2 is equal to cube root of this. Okay, cube of this. So this is our relation. This is our relation for sigma. If sigma is an out of K, then it satisfies this relation. But if this sigma is in, if it is in GKF, means that if it fixes every element of F naught, if sigma belongs to GKF naught, F naught is the set of rational numbers, means that if on F naught sigma fixes every element of F naught, okay, इसका नाम मैं 1 रखूंगा, then 1 gives then this 1 give it is sigma 2 is 2 because it is in GKF naught. On F naught sigma fixes every element of F naught. F naught is the set of field of rational numbers, and on this side it's equal to sigma of cube root of 2 whole power 3. So that means sigma of cube root of 2 is equal to 2 power 1 by 3 cube root of 2. Okay, मैंने इस 3 को यहाँ ट्रांसफर किया. So this is the value of its value is cube root of 2. Okay, so that means it fixes also cube root of 2 because this has only 3 values because you are taking the cube root of 2, but we have to take only the real value, which is cube root of 2. So these two values are same. This is also the real cube root of 2, real value of the cube root of 2. This one is also the real cube root of 2. So it means that it also fixes this element. If sigma fixes rationals, then it will fix the real value of the cube root of 2. If it fixes rational, then it will fix the real value of cube root of 2. This is very important. Okay, but then you will see that it will fix every element of K. So now let's take any element of K. Let T belongs to K. Then what's T? What's the representation of T? Then this T is equal to, then T is of this form. T is equal to alpha naught, जो हमने भी दिखाया आपको, alpha 1 cube root of 2 plus alpha 2 cube root of 2, it is square. Okay, this is your T. Now we will find sigma T. Let me erase this page now. So you have seen that this T has this representation because it's in K. Then what is sigma of T? Sigma is automorphism, which is equal to sigma of, and वहाँ पर आप लिख दीजिए where alpha naught, alpha 1, alpha 2 they are in F, they are rational numbers. So it's equal to sigma of T minus alpha naught plus alpha 1 cube root of 2 plus alpha 2 cube root of 2 square. This is our this. Now there is sigma is automorph, it is sigma of alpha naught plus sigma of alpha 1 cube root of 2 plus sigma of what, alpha 2 cube root of 2 square. Okay, this thing. This alpha naught is rational, so sigma of alpha naught is alpha naught plus. Here again we can apply the property of automorphism. It's equal to sigma of alpha 1 into sigma of cube root of 2 plus, this is the product of three elements, alpha 2 then cube root of 2 into cube root of 2. It's equal to sigma of alpha 2 to sigma of cube root of 2 sigma of cube root of 2. This thing, it's equal to alpha naught plus, since sigma of alpha 1 is alpha 1 and sigma of cube root of 2 is cube root of 2 plus sigma of alpha 2 is alpha 2 and sigma of cube root of 2 is cube root of 2, sigma of cube root of 2 is cube root of 2, so it's cube root of 2 whole square. So this same as T. So that means sigma of T is T for all T in T. Okay, thus sigma of T is equal to T for all T belongs to K. So which means that sigma is equal to I, the identity automorphism. तो जो भी automorphism इस G के F में है वो identity है. So it contains only one element, identity automorphism. So that is your G K F is a singleton set. It contains only one element, and that is identity automorphism. Now we find the fixed field of this. Now what is fixed field? Now fixed field of this group. By definition, those elements of K such that sigma of A is equal to A for all sigma belongs to this group of automorphism, and which is equal to the identity. इसमें सिर्फ एक ही automorph identity. Yes. And this is equal to A belongs to K, वो elements K के जो sigma of A equal to A for all sigma belongs to GKF. अब GKF में सिर्फ identity है, that means I of A equal to A. अब I कितने एलिमेंट्स को फिक्स करे की I is identity automorph, ये हर किसी एलिमेंट को फिक्स कर रहे हैं ना, so that means it's equal to whole key. So that means it's not equal to F, जो मैंने आपको बताया था, ये F के बराबर नहीं है. The fixed field of GKF need not be equal to F. It may be bigger than F. It may be bigger than F. It may be bigger than F. Okay, so thus we have seen that this F, it is strictly contained in the fixed field of the group of automorphisms. Okay, it's not equal to F in general. Now next we have an exercise. Let F be a subfield of K. Then show that this F is always subset of this fixed field of that automorphism, which are fixing K. Okay. Okay, we take any element here and we'll show that that element belongs to this. That means that element will be fixed by every automorphism of GKF. So that it is very simple. अगर आप इसको देखना चाहोगे, let A belongs to F. आपको प्रूव करना A इसमें है, K आप GKF में. अब चूंकि A इसमें है, it means that sigma of A is equal to A for all sigma belongs to GKF. क्योंकि GKF की डेफिनेशन ये है कि इसमें वही ऑटोमॉर्फिज्म्स है जो F के एलिमेंट्स को फिक्स करे, और वही तो एक्चुअली K GKF की डेफिनेशन है. सो विच मीन्स दैट दिस A belongs to K of GKF. So thus F is subset of K of GKF. F is subset of, and we have seen that the strict inclusion here in the previous example, and also we have seen the equality in one of our example, है ना, जो हमने इससे पहले वाले एग्जाम्पल किए वहाँ पर हमने इक्वालिटी देखी, यहाँ पर हमने स्ट्रिक्ट इनइक्वालिटी देखी. सो इन जनरल दिस K is subset of KGKF. KGKF. This we have seen. So thus F is subset of K of GKF. K of GKF. Where this K is a subfield, this fixed field of GKF. GKF is the group of automorphisms fixing the elements of F. So we have one more example. Let's here एग्जाम्पल से आपको थोड़ा ये समझ आ जाएगा कि हम क्या कर रहे हैं. Let F naught be the field of rational numbers. Let F naught be the field of rational numbers. Be the field of rational numbers, and let omega is the fifth root of unity. That means omega power 5 is equal to e power 2 pi iota divided by 5. So that is, you can see this omega power 5 means e power 2 pi iota, which is equal to 1. So that is, omega is the fifth root of unity. Okay, is the fifth root of unity. Is the fifth root of unity. Is the fifth root of unity. And one can see that this one, since omega power 5 is equal to 1, so omega 1 is the root of this omega power 5 equal to 1, then we have seen that we can find all the 5 roots actually. One root is the 1 and other 4 roots are the complex roots that can be easily found, and we can also find the equation of those 4 roots. How we can find the equation of those 4 roots? So we have this equation actually. We have x पावर 5 इज इक्वल टू 1, जैसे आपने मतलब 12th क्लास में किया है, इसकी 5th रूट्स ऑफ यूनिटी आपको निकाली। इसका एक रूट 1 है ना, एक रूट इसका 1 है, तो बाकी 4 रूट्स की इक्वेशन आप कैसे निकालोगे? हाउ टू फाइंड द इक्वेशन ऑफ अदर 4 रूट्स? एनी आइडिया? एक रूट इसका 1 है, obviously 1 power 5 is 1. So we can do this. Since x equal to 1 is the root, so x minus 1 must be the factor. Or first you write it as x power 5 minus 1 is equal to 0. But x minus 1 is the factor, so it must be x minus 1 times some other polynomial. So we want to find that polynomial. What's here? The product should be equal to x power 5 minus 1. यहाँ पर आपको वो पॉलिनोमियल लिखनी है, जब आप प्रोडक्ट करोगे ना इन दो का, वो आना चाहिए x पावर 5 minus 1. तो फर्स्ट टर्म है x पावर 5, so I must have here x power 4. But if I write here x power 4, I must have the term x minus x power 4, which is not here. So this is here minus x power 4, so I must have another term plus x power 4, so that minus x power 4 and plus x power they will go. So I will add here x cube, then x cube into x plus x power 4, and this is here minus x power 4, these two, and this one is plus x power 4. Okay, these two will go down. But if whenever I write x cube here, then I will have one more term, that's minus x cube. So I must have plus x cube, so I will write here plus x square. But by writing x square here, there is a term which is minus x square, which is not here, so I must have plus x square. But there is minus x now again, so I must have plus x, so I will write here plus 1, then plus 1 into minus 1 is minus 1, that's there. So it's like this. Or you can divide x power 5 minus 1 by x minus 1, you will get this quotient जो मैंने यहाँ पर लिख दिया, x power 4 plus x cube plus x square plus x plus 1. Or you can do directly like this. Okay, so this x power 5 equal to 1 has 5 roots. One root is the 1, that's the root of this factor, and the other 4 roots are the roots of this equation. Another 4 roots are the roots of this equation. So thus, since omega is the 5th root of unit, so thus omega satisfies this equation. Thus मैं इसको erase करूँ, thus omega satisfies this equation, x power 4 plus x cube plus x square plus x plus 1 equal to 0. Okay, which omega satisfies this. We don't need to write here 0. Satisfies का मतलब ये है कि 0 satisfies this, which is over f naught. F naught means a field of rationals, because the coefficients of x is coefficients of x4, x cube, x square and x, they are all equal to 1 here. So it's a polynomial over f naught, which is the field of rational numbers, and this polynomial is irreducible, over f naught, and this you can see by Eisenstein's criteria. अगर आपने किया होगा वो Eisenstein's criteria किया आपने वो, this polynomial is irreducible. Okay, so you take this, आप इसका वैल्यू कुछ लीजिए, जैसे f of x equal to this polynomial x4 plus x cube plus x square plus x plus 1, then you will write f of x plus 2, because we know that f of x is irreducible if and only if f of x plus 2 is irreducible. तो उससे शायद आपको कुछ आइडिया मिल जाएगा, या इन जनरल एफ ऑफ एक्स प्लस पी आप देख सकते हो. आई थिंक एक्स प्लस 1 will work, and you can see the proof of this part in any book. This polynomial is irreducible by Eisenstein's criteria. This is an irreducible polynomial. So whenever we have an irreducible polynomial, and omega is the root satisfying this irreducible polynomial, but this one x power 5 minus 1 is not irreducible because it has two factors. One is x minus 1 and second is this factor. This is not irreducible, but this one is irreducible. Okay, so thus we have this k, which is equal to the smallest field containing f naught and omega, is of degree 4, is of degree 4 over f naught, because degree of this polynomial irreducible factor, जो irreducible polynomial है उसकी degree 4 है, because of this reason. The minimal irreducible polynomial satisfying by omega is this one, x4 plus x cube plus x square plus x plus 1. Its degree is 4, so that's why the degree of this, that is we have this actually. Degree means this one, the dimension of k over the field f naught is equal to 4. This thing is 4. And what are the elements of f naught omega? That's also important. What are the elements of f naught omega? And how can we find the automorphisms of k which fixes the rational numbers? So obviously this field is generated by omega and f naught, and since on f naught those automorphisms fixes the elements of f naught, so we just find the value of those automorphisms on omega only, at omega. क्योंकि हमने अगर ओमेगा पर उसका वैल्यू निकाला, हम ओमेगा स्क्वायर पर भी निकाल सकते हैं, ओमेगा क्यूब पर भी, ओमेगा 4 पर भी. तो इसकी वजह से हम उसकी मदद से हम k के हर किसी एलिमेंट पर उस ऑटोमॉर्फिज्म का वैल्यू निकाल सकते हैं, अगर हमने ओमेगा पर इसका वैल्यू निकाला और जो f नॉट को फिक्स करे. Now for any sigma belongs to out of k, so clearly this sigma fixes the rationals. This is trivial. So then this sigma belongs to gk f naught. That's trivial. That we don't need to impose condition here. This sigma should be belongs to gk f naught because it's always there. Because every automorphism fixes every rational number. Then this sigma, it belongs to g k f naught. G k f naught. नेक्स्ट पेज, इसको मैं अब